Okay, I think it's time to start. Please sit down, those who are still standing in the door. Good morning, everyone. Welcome to our faculty colloquium, which this time will be really remarkable. As a lecturer, we have Professor Andrzej Wróblewski from our faculty, who also graduated from our faculty and whose scientific career was connected to this university. Not only to this one, but mostly. Professor Wróblewski is a particle physicist. Recent years devoted to history of physics. You probably know all his books, which are here. Something like History of Physics, which is a textbook, I hope, to young and less young. He's preparing next ones. Dictionary of Polish Physicists, about to be completed now. And before those, several others we all probably know. And then the great thing is that we have a chance today to hear about a discovery, probably the largest discovery in our Polish university physics at least, from a person who was magna pars fuit, was a large part of it, an eyewitness. That is very rare, so it's good that we came here. Well, many of us, maybe not as many. Please take a seat. There are still places here. So I should stop this introduction because most important is ahead of us. Thank you so much, and Professor Wróblewski, the floor is yours.
I'm old enough to remember those years, those events that I will be talking about, and that's why I'm particularly attached to the problem of discovery of hypernuclei. Most of you, the older generation at least, remembers our historic building at Hoża 69. This is beautifully drawn here. But for the youngest generation, of course, this is archaeology already, ancient history. But the discovery which I will be talking about took place just in this particular building. Okay, so now let's remind by ourselves the theme of the topic of my talk. The first hypernucleus was discovered in September 1952, so almost exactly 70 years ago, by Marian Danisz and Jerzy Pniewski in the University of Warsaw Physics Laboratory at Hoża 69, a ground floor in this beautiful building which you have seen. And what is very important is that this discovery happened during a time of confusion, which I will be talking about. Confusion concerning the newly discovered strange particles, heavy and stable particles, which were later named strange particles. And it appeared that the study of hypernuclei discovered at Hoża 69 was of considerable help in understanding the properties of strange particles. Now, the strange particles were originally called V particles, because they left traces in the photographs of cloud chamber in the form of the V letter. You have seen in upper photograph you see marked with letters A and B, and the problem was that these particles were quite copiously produced. The cross section was of the order of few percent of the for the production of pions. So the mechanism of producing them was quite strong. There was strong interaction. And again, if the same mechanism was responsible for their decay, the lifetime should be 10 to minus 21 seconds, their lifetime. However, experimentally, the lifetime was larger than 10 to minus 10 seconds, so there was 11 orders of magnitude discrepancy, and no one knew how to explain it. The particles were mysterious for one more reason, that after the first two examples discovered in 1947, for the next 2 years, no other example was discovered. So some people even tend to think that perhaps it was some misunderstanding of cloud chamber photographs, etc. So, unfortunately, in 1950, another discovery of V particles came, and it added to the confusion. Added to the confusion because there was a proliferation of these very strange particles. And I am showing you here the table, the original table from the paper published in December 1952. So approximately the same time that hypernuclei were discovered. And as you see, there were about 10 particles discovered, most of them with strange question marks, and only 3 were regarded to be as firmly established, and they were called V01, tau meson, and V02. For the other particles, the data were quite scarce. Now the problem was the discrepancy between their lifetime and large cross-section. And the first idea of how to explain it came from Abraham Pais, who on the 1st of June 1952 published a paper in Physical Review, some remarks of on the V particles. And he said the following: one can explain this strange discrepancy provided they are produced only in pairs. And then we don't need any additional interaction. Conventional interaction would be enough if particles are produced in pairs. And this is very easily explained. For example, all the old particles, protons, neutrons, pions, etc., have this some new quantum number equals to 0, and all new particles have this new quantum number equal to 1. And then the sums of n initial and n final must be both even or both odd in strong and electromagnetic interactions. And so then he provided a nice explanation. However, there was a problem. This even odd rule that Abraham Pais proposed allowed reaction of the type nucleon plus nucleon gives 2 V's. They were called later lambda particles, as you know. So this reaction n plus n goes to lambda plus lambda was possible, which we now know, and this is absolutely impossible. So anyway, so this was the problem, to find out whether this really goes on, like Pais predicted, that particles are produced in pairs. And unfortunately, experimental evidence was against pi production of these particles. And I am quoting here from 2 papers, one from Berkeley, another from Caltech, experimental papers. Both were published in January 1953, but submitted in September 1952, which was just about the time that we will be talking about. And in both cases, the authors concluded that the frequency of the observation of V particles contradicts the hypothesis that V's are created only in pairs. And again, Lighton and others from Caltech concluded that V particles are generally produced singly and not in pairs. So the mystery deepened with this. And this was so much confusing that there was a conference, so-called famous Rochester conference in December 1952, and Robert Oppenheimer, who was asked to give a conclusion, said the following: I hope our grandchildren, when they attend the 2038 conference in Rochester, will take it for granted that they know these things. So this was quite pessimistic because it was so confusing, so that really no one expected this to be solved in near future at the time. So this is the explanation of how confusing the time was in the fall of 1952, when the discovery I will be talking about took place. Now let me talk about the discoverers. The two discoverers, you know the name, but I will first present them as they were seen in 1952, because our picture of them nowadays is completely different. But in 1952, they were seen otherwise. Marian Danish was called Mr. Danish. He was little known electrical engineer. He joined Hoża in 1948, and after approximately 1 year, he was sent by Pieńkowski to England, and he spent more than 2 years in England. So he came back in May 1952. So he was out, he was absent, he was not known, and he was simply called Mr. Danish. Jerzy Pniewski had just recently obtained a PhD on beta spectroscopy in June 1951, but he was known mainly for serving in restoring and building Hoża 69 building after the World War II, because he served as a right hand of Pieńkowski, the founder and director of the institute. But he was not known for his scientific achievement because he didn't have any yet. Now, they were both quite advanced in ages. Pniewski was 38, Danish was 41, but of course their career was destroyed by the war, occupation, so they lost about 10 years, and this explains why Pniewski obtained his PhD only at quite advanced age, which is unheard of at present years. Now, I told you that Danish was simply called Mr. Danish, because at that time there were few professors at Hoża. Stefan Pieńkowski, of course, the founder and director of the institute, and then director of the Institute of Experimental Physics. There were two more professors in experimental physics, Andrzej Sołtan and Leonard Sosnowski, and that was it. And then there were some junior staff, like Jerzy Pniewski. In theory, there were again 3 professors, Leopold Infeld, Wojciech Rubinowicz, and Czesław Białobrzeski. So there were 6 professors, plus a couple of younger people. This was the picture of Hoża 69, 70 years ago. Now, the discovery took place in September 1972, and it was very beautifully described later, of course, by Jerzy Pniewski in his autobiographical reminiscences. This was written in Polish, so I translated into English a few sentences to show the climate of this discovery. So Pniewski wrote the following: late in the evening of September 19, we began to analyze the recorded events one by one. Remember that Danish came in May 1952, so this was just a few months after he came and brought from Bristol, where he was, some emulsion plates irradiated with cosmic rays in a balloon flight. So we began to analyze the recorded events one by one. Suddenly, Marian exclaimed, "Look, what a strange animal," and showed me the 2 stars connected by a prominent and quite thick track. It was obvious that one of the stars was due to a disintegration of a heavy emulsion nucleus, silver or bromine, by high-energy cosmic radiation proton. The nucleus was split into small fragments, and only one of them, distinct by its quite long track, seemed to have mass considerably larger than the others. Its track ended with a 4-pronged star, which indicated its spontaneous decay. But then the lifetime of the fragment, estimated from the length of its track, was unbelievably large for such an excitation. So this was this historic photograph. You see the primary star, and the particle originated from cosmic rays. Doesn't work somehow. I will use the mouse, but perhaps doesn't work. No, it doesn't work. So anyway, you see the particle which is marked with P and then red arrow, and then there is a large star and the fragment F, called F, quite long track, disintegrating into secondary star called B. And this was quite long track. You have a scale 50 microns or micrometers as we call now. So the lifetime was quite long. So Wróblewski continued. We spent nearly 3 weeks on endless and heated discussions, during which we eliminated various explanations of the observed inconsistencies. Twice a day we went for coffee to Café Niespodzianka. It's a historic cafe, square of the Constitution, very near to Hoża. And it was there that we suddenly began to see the light. That so large energy released in the secondary star was comparable to the energy of annihilation of the pi minus meson, the particle discovered 5 years earlier. The first hypothesis was that the fragment carried a bound pi minus meson, similarly to an electron bound in an atom. This very attractive hypothesis had to be rejected because it was improbable that the fragment could capture and carry away one of the mesons produced in the high energy collisions. But we are only one step from the proper interpretation that the fragment contained a bound V01 particle. The V01 particle was discovered in 1951, a year earlier only, by Armenteros, but no one expected that it could be bound in atomic nucleus with protons and neutrons. So after about 3 weeks, they decided that this is correct interpretation. And Wróblewski continues, we sent letters to Heisenberg, Powell, and Skobielcyn. Now, why these 3 physicists? Heisenberg, everyone knows the name. Powell was the host of Danish in Bristol, an authority in Martian studies, and quite recent Nobel Prize winner. He got the Nobel Prize in 1950. And Skobielcyn. This is a surprise. Why Skobielcyn? Who is Skobielcyn? Who was Skobielcyn? Well, Skobielcyn was a Russian physicist who was doing some work in cosmic ray physics, not very well known, but probably Danish and Wróblewski were advised to send one of the letters also east, not to be then charged that they are only corresponding with the west. So they sent this letter to Skobielcyn. In fact, it's not known whether the letter reached Skobielcyn because the answer never came. Anyway, but the letters to Heisenberg got there, a letter to Powell also. Danish and Wróblewski didn't know Heisenberg personally, but they knew Klaus Gottstein, who was working with Danish at Bristol. So the letter was sent to Gottstein, who showed the contents of this letter to Heisenberg, and then Gottstein wrote back. And now I will show you the answers. Now, in order to be on the safe side, they persuaded Professor Andrzej Soltan. Remember, they were young physicists. Professor Soltan was already a professor, and he was member of the Polish Academy of Sciences, to accept a short notice on the discovery. And this was communicated by Soltan at the meeting of the Polish Academy of Sciences, the proper section, of course, physical section, at the meeting of October 20. So about 1 month after the discovery. And this was a preliminary explanation of what they found. In this way, they wanted to secure their priority in future discussions. Now, this was the letter to Powell. Of course, it's a copy of it. It's hard to read it, so I wrote it here in larger letters. And it read as follows. Dear Professor Powell, It's more than 4 months that I am back in Warsaw. From September, the work has begun, and I hope we have some prospects for the future. I have easily found people who are interested in the Martian work. 3 scholars are active since the end of September. Problem of microscopes seems to find a satisfactory solution. With this letter, I enclose a short note concerning a star, a rather exceptional character. We have worked on it with my friend J. Pniewski, who will, I hope, continue to work with me in plate technique. Pniewski, of course, was not known to Powell. If you find the whole problem not unreasonable, we might send later a fuller account to Philosophical Magazine. Philosophical Magazine was, at that time, the main journal for particle physics results. We would be very grateful for your suggestion and criticism. Yours most sincerely, M. Danish. This was quite official letter. Danish was a junior physicist in Bristol, in Powell's laboratory, so he very much respected Powell, of course. Now, the first answer came from Munich, from Gottstein or Heisenberg, and again, I will present it in larger letters. It was sent on 10th of November. Dear Danish, thank you very much for your letter of October 26 and the preprint of your paper, which I think is very interesting. Professor Heisenberg has also read it with great interest. He agrees that the event cannot be explained as the delayed disintegration of an excited nucleus, since the time 10 to minus 11 seconds is much too long. On the other hand, the probability for the event being a delayed sigma star is extremely small too. The binding energy of a pi minus meson in the K shell is of the order of 1 MeV, whereas the average energies of the meson ejected in the disintegration at A, this primary star, are apparently much greater. So it is unlikely that a pi minus meson would have been captured by the fragment. But even if it had been captured, it would have to be expected to interact with the nucleus within a time much shorter than 10 to minus 11 seconds. Your suggestion that the event might be explained in connection with the V01 or a similar particle seems to be very reasonable, however. The V01 particles appear to be different from the nuclear force mesons in that they may be created and annihilated only in conjunction with their antiparticles. Remember, this was the hypothesis by Pais. In your event, the V01 may have been separated from its antiparticle, which flew off in a different direction and was left within the fragment where it decayed after its lifetime had elapsed. I wonder what the future will teach us about all these funny particles. With best regards, yours sincerely, K. Klaus Goldstein. A letter from Powell was much restrained. Again, this is for your convenience. Dear Danish, thank you very much for your letter of this 26th of October. The event is certainly most striking, but I feel that you would be well advised not to publish it at this stage. In spite of the most remarkable precision with which the heavy particle ends its range at the point of origin of the second star, you still have to meet the objection that you are dealing with a chance juxtaposition of unrelated events. Because of this, I think that it would be best either to wait until a second example of the same phenomenon is found, or to publish a photograph of it with a minimum of descriptive material. There seems to be no point, for example, in giving a detailed description of the big star from which the heavy particle was emitted. Powell, of course, knew about this short note that was already sent and published in the proceedings of Polish Academy of Sciences, but apparently he didn't take it seriously, so he advised not to publish it at this stage. And now something unexpected happened. Namely, from London, not from Bristol, but from London, came a letter from Mr. George, who was a physicist there, known to Danish. Dear Danish, we have recently found a similar event, and this was a rough sketch by hand, and we were told that you have similar event, and perhaps we could publish it jointly, because two events are better than one, etc., etc., etc. Now, remember that Danish and Pniewski were junior physicists at that time. They were not known to the world, so they took this suggestion of two events in the same paper quite seriously. And so Danish answered the following on 28th of November. Thank you for your letter of the 19th November and the news concerning your case of a delayed disintegration of a heavy fragment. Obviously, two events of such a kind are much better than one. And I quite agree that it is a good idea to publish this jointly in a note or letter in Philosophical Magazine. Not to lose time, I will suggest that you would write a rough draft of the letter or note in question and send us a copy before further publication, as we may have some suggestions or remarks to make. So they were quite close to the idea that perhaps both events should be published in the same paper. But then Powell, who supervised it from England, from his capital of emulsion physics in Bristol, said no, shouldn't go this way, because he knew that the Imperial College physicists from London had their event much earlier than Danish and Pniewski, but he didn't understand it, put it aside, and only took it from their drawer after they learned about Danish and Pniewski event and about their hypothesis also. Danish didn't know what was going on in England at that time, so he answered to Hertz in London, sorry. Dear Hertz, after receiving a letter from Menon concerning Powell's proposition, we have sent the material related to our case to Bristol and left all the decision concerning the publication to Powell. So I hope all is okay. Of course, we are pleased to have another note in the same issue of the Philosophical Magazine supporting our observation. Powell, who had an authority as Nobel Prize winner, etc., said no, it cannot be that way that two events are published in the same letter. Danish and Pniewski have clear priority, and the London physicists have found it worth publishing only later after they learned. So there should be two notes with very clearly given priorities. So the first event was published in Philosophical Magazine, and you see this was stressed that this is received on December the 1st, 1962, and that the same issue of the Philosophical Magazine was the second event, but received December 15. And in this second event, it was already stated that soon after Dr. Menon of Bristol University had informed us about event found by Danish and Pniewski, a similar observation was made in this laboratory. So in this way, thanks to Powell, the priority of Danish and Pniewski was established and fixed. Otherwise, as you see here, the second event had 4 authors from London, and so eventual paper with 2 events would have 6 authors and all will be smeared out somehow. And very soon, in fact, the third event was found in France, in Paris, by Cussard and his collaborators, and it was published and presented at the proceedings of the French Academy of France of Science in January 1953. So that was it, 3 events, and nothing more for the next half a year or so. But 3 events were already enough to take it seriously, and Powell, however, remained skeptical for several months. In the letter to Nature, which he published in September 12, he wrote the following, among other things, of course. Further examples have now been observed of the process first observed by Danish, he still didn't recognize Pniewski, in which a heavy nuclear fragment ejected from a nuclear explosion reaches the end of its range and disintegrates. It appears that pi mesons are frequently emitted as one of the products of the secondary disintegration. It is possible that these events are due to the presence in the nuclear fragment of a nucleon in an excited state, but alternative explanations cannot at present be excluded. However, this didn't last long, and after several months, in March 1954, he was quite convinced that this is a very important discovery, and he wrote again in Nature. The original discovery suggested that lambda hyperons, in the meantime the V particles were called lambda hyperons, can exist not only as free particles but also bound within nuclei, was due to Danish and Wróblewski. Wróblewski was suddenly finally recognized by Powell. And the excited hydrogen atom, to use the simplest example, consists of a proton and an electron in a state of higher energy than in the normal atom. The analogy might then suggest that the excited nucleon consists of a proton and an associated pi minus, that the lambda zero is a composite particle. Such a view could not have been finally excluded, while our knowledge was confined to the decay of the free particle, lambda particle. This consideration suggests that the lambda particle is an excited nucleon in a different sense from that suggested by familiar analogies. We are entering a new field where basically new concepts remain to be established. So this was the final acceptance that this is a very important discovery. It somehow cleared up that lambda is a new particle and not the excited state, or with some slightly longer lifetime. And then in April 1954, there were already 17 known events about in laboratories all over the world. And the summary was prepared by two Italians, Brilli and Levisetti. And the conclusion was, in none of the cases the total energy release in the disintegration of the fragments is inconsistent with the hypothesis first suggested by Danish and Wróblewski, that a neutron in the fragment is simply replaced by a lambda zero. Now let me add a very short personal note here. This is April 1954. I joined Danish group about half a year earlier. I was his first master student, so to say. There were some people who joined him earlier, Ewa Skrzypczak, for example, but she was doing her master thesis with Pienkowski. But I was the first master student of Danish, and I had at that time 5 events in my disposal. I had to analyze 5 events. One statistics was 17. So I had in my hands, so to say, about 1/3 of the statistics. So this was really a front line of research. So I wrote this thesis, and it was then published in Nuovo Cimento. Now, of course, other people joined. This is much later now, 1957, sorry. The first theoretical paper or survey of hyperfragment experimental data was prepared by Filipkowski, Girula, and Zieliński. And they had already about 120 at that time events, because the statistics grew quite rapidly. And finally, in 1963, hypernuclear physics was regarded officially as a new branch of physics. There was the first international conference on hyperfragments in Saint-Sergue in New Geneva in Switzerland. And there were 68 participants from 14 countries. There were 17 talks published in the proceedings. So this was already the recognition that this is a quite distinct branch of nuclear physics. And again you see, and you will see it still more in the next slides, this photograph, microphotograph of the first hypernucleus found by Danish and Wróblewski. This became an icon in a sense. it was repeated in many, many reviews, papers, etc., etc. The first double hypernucleus was also found in Warsaw in 1963. There was a big collaboration, 8 collaborating labs, 8, and just by accident or by luck, the first double hypernucleus concerning 2 lambda particles was found in Warsaw, and that's why in the joint publication you see that the authors are Danish, Garbowska, J. Piewski, Jerzy Piewski, Tadeusz Piewski, he was a nephew of Jerzy Piewski, and Janusz Zakrzewski, who was at that time also working on hypernucleus. Now, this hypernuclear physics grew quite rapidly. As you see, first there were just few papers published every year, and then it grew up to the level of about 50, 60 papers published per year. And there was a renaissance even. This is a cover of Cell Courier from April 2003, in which you see the iconic picture of the first hypernucleus in the cover. And then there was long articles on hypernuclear physics program in different countries, in Germany, in USA, Russia, Japan, Italy, etc. And it still goes on, it's expanding. And just to prove it, I show you here a paper which I found published in October this year, so about 4 weeks ago. Deformation and hyperon halo in hypernuclei. So this is quite active field even now, after 70 years. Now, I showed you, I described you the discoverers as they were seen in 1952. And of course, now we see them differently. And let me start from Marian Danish. Perhaps not all of you know that he was born in 1909 in Paris. He was the son of the Polish-French physicist Jan or Jean Kazimierz Danisz, who made the first beta spectrometer in 1911. He was born in Paris, but then came to Warsaw, finished the famous Batory High School in Warsaw, then studied electrical engineering at Warsaw Polytechnic. But while being a student at Warsaw Polytechnic, he worked as in Warsaw Radiological Laboratory because it was headed by Ludwig Wertenstein, a friend of his late father. So in fact, he had some success. He discovered radioactive isotope of fluorine and co-authored 2 papers. But then he was no longer interested in physics. In the years 1937-38, he worked as an electrical engineer in a state institute. And then after the war, he somehow survived the war. 1945, 1948, he taught electricity in a private technical school in Warsaw, the so-called Wawelberg-Rotwand school. And then he decided, he knew already that the Wawelberg-Rotwand school is to be dismantled by the authorities because it was private school. So he decided to go back to his roots, so to say. He came to Hoża Street and asked Pienkowski to take him as an employee. Pienkowski agreed, and almost immediately he sent him, after a year, to England to learn new things about nuclear physics, because Pienkowski himself, of course, was an expert in optics, but he had a very open mind, and he wanted to extend area of research in Hoża. So that's why he sent Danisz to England and also Piewski to England. Danisz first went to Liverpool, but he didn't like it there. So he went to Bristol, and then he stayed about 2 months, learned about emulsion technique in Powell's laboratory. It was #1 laboratory in the world. And while being there, he even claimed discovery of a new particle, which proved to be wrong, with Owen Locke and Gilbert Jekutieli. Jerzy Piewski had completely another life. He was born in 1913 in Płock. He was a son of a high school teacher. He studied mathematics and later physics at University of Warsaw. He started career in molecular optics just before the war. He even published 2 papers in 1938, not very significant papers. And then, as I already mentioned, he was sent by Pienkowski to Liverpool to study beta spectroscopy. He came back, obtained in June 1951 PhD in nuclear spectroscopy. And then after a year he was persuaded by Danish, with whom he communicated in England, because they were both in England, to join him in cosmic ray studies using nuclear emulsion. And then unfortunately he had to stop research quite soon after the discovery, because Pienkowski died on 20th of November 1953, and the next day, November 21, Piewski was made director of the institute. So he had heavy administrative duties for several years and couldn't participate in decay. Now, Marian Danish, let's take a more human side, had very little physics background, because, as I said, he was a student in Warsaw Polytechnic of electrical engineering. But he had fantastic intuition, unusual imagination. He hated administration, formalities, lecturing, etc. Loved fast driving and hunting. He was chain smoker of cigars, cigarettes, and pipe, and loved good food. During his fast driving, he quite often killed small animals such as hares, and this lower photograph showed him when he visited us, me and my wife. We were spending holidays in at Augustów Lakes, and he came to visit us, but on the way he killed a hare, and of course he was, as a hunter, he was quite expert in preparing it for food, and he had a fire, and he was just preparing this hare. It tasted quite well, I must say. Now, what about Jerzy Piewski? He, on the contrary, had solid background in physics and mathematics. He was extremely well organized and systematic. He was a good lecturer, competent and efficient administrator. He loved to entertain friends with magic tricks and puzzles. And he never smoked, but loved good cognac. I knew both of them, and I had the luck of being friendly with both of them. That's why I'm allowed to say such things about them. Now let me conclude with the following. Paweł, in the after-dinner talk at Saint-Cirque, said the following: I am reminded of a famous remark of Napoleon. Whenever he was presented with a young man for military advancement, he invariably asked the question, is he lucky? This was by no means a casual inquiry. The important quality for which he was seeking was, does this man put himself in a situation where he can be lucky? If you fail to put yourself in a situation where it is possible to have good fortune, then you cannot have any success. If you do, you may. And there is also a well-known statement by Louis Pasteur. In the field of observation, chance only favors those minds which have been prepared. And now, what about Danish and Piewski? The first hypernucleus was found just after the start of scanning of new emulsion plates in the new laboratory of Little Experience. This was an incredible piece of luck, or a miracle. The first double hypernucleus again was found in Warsaw, which was, as I said already, one of the 8 elaborating labs. This was again an incredible piece of luck, or another miracle. My conclusion was that both Danish and Piewski were lucky and well prepared, both. Later, they discovered hypernuclear isomerism, and Piewski, Danish was and then sick and didn't take part in research. Wróblewski himself alone initiated hypernuclear spectroscopy. We didn't manage until now to persuade Polish postal office to issue a stamp commemorating this discovery. At 40th discovery, anniversary of the discovery, we persuaded to publish a postcard with a stamp. This is, of course, a drawing of a stamp, and you see again the iconic photograph of the first hypernuclei. There was also a special stamp that postal offices used in for different occasions, and you again see this stamp here on original postcard. And this will be all. Thank you.
Thank you very much for this beautiful lecture. Of course, I remember both Marian Danish and Jerzy Wróblewski, but I was too young to be in good relations with them. Now we have time for questions.
So I would like to understand really where the experimental data came from, because I understand that this first emulsion plate was brought from Bristol. Yes.
Yes, there was a balloon flight to about, if I remember well, about 30 kilometers. At that height already, the intensity of primary cosmic radiation is enough to interact with atoms of the atmosphere, of course. Now, if you put a plate, number of plates of emulsions with the balloon, and the balloon stays there for several hours, then the emulsions get irradiated. Then after the balloon comes down to Earth, these emulsions are developed, etc., and then distributed among laboratories which took part in preparation of the flight. In the case of the first emulsion plate Danish obtained as a present, of course this was otherwise. This was just a gift from Powell, because Warsaw Laboratory didn't exist, so it couldn't take part in the balloon flight. But then later, for several years, the same procedure was repeated. Namely, large collaborations were working together to prepare emulsions, send them to some height of 30 or more kilometers, and then analyze the emulsions.
Other questions or comments? No, you did not mention that they were proposed for the Nobel Prize, but never got it.
Oh, yes, they were several times proposed for the Nobel Prize in physics. They didn't get it. On my count, this was about 10 or more times that they were proposed. Why? I don't know. One of the reasons was that we still at that time lived behind the Iron Curtain, on the wrong side of Iron Curtain, so I want to say. And for example, there were numerous cases when Danish and Wróblewski for the first years were not allowed to go to foreign conferences. There was a conference in 1953, the first conference in Bigorre in France. Danish was invited, but he didn't get passport and he couldn't go. And then another conference, he couldn't go. Saint-Cergue, of course, was 10 years later, and then the situation in Poland was a little bit more relaxed. So Wróblewski went there, and also Danish to Saint-Cergue. But in the first years, they were strictly bound to Warsaw, so to say. This was one of the reasons, perhaps, because they were not known. They were not known to physicists, to the physical world, only from publication, but then, of course, there are many publications.
Yes. No,
Both Danish and Wróblewski were sent to Liverpool, you said.
Yeah, I can give you the reason why they were both sent originally to Liverpool. In Liverpool, at that time, was Józef Rotblat, who went to England in the September 1933. He was a Jew. He saved his life in a sense. He was sent to Liverpool to study. He was sent by Wertenstein because he was working in this radiological laboratory which I mentioned already, by Wertenstein. And Danish, as I mentioned, also worked there, so he knew Rotblat. He was his colleague, the difference being only that Rotblat was employed there, and Danish was a student of Warsaw Polytechnic, and he appeared there from time to time, but they knew each other already. So this was the reason.
Can you remind us the title of your master thesis?
My master thesis had the title "The Analysis of Stars Leading to Hyperfragment Production." It's published.
Other questions or comments?
By the way, while this was the topic, as I said, as I explained, there was this discrepancy, and on the one hand, the hypothesis of production in pairs, and on the other hand, experimental evidence seemed to be against this. So Danish asked me to analyze primary stars to see whether some of them could be K heavy mesons, and I found 2 in 5 stars. 2 tracks which had a mass of approximately that of K mesons. So this was the result of my master's thesis.
Yes, another question.
If we want somehow to summarize the impact of this discovery for like present day understanding of particle physics, how would you summarize it?
Well, the impact was about 2 years after the discovery, strange particles became already well established. The name strange particles was invented. Also, the strangeness was invented by Gell-Mann, that was 1955, so 3 years later. And at the beginning, as Powell stressed in his note into Nature, this was the argument against treating this V particle as an excited, very funny, excited state of a nucleon, and not as a separate particle. So this was very essential. Secondly, then after the years when of course, experimental evidence grew, then there was another problem, because the presence of lambda particle inside the nucleus enabled us to observe, produce and observe, quite exotic nuclei. Because then the presence of lambda inside the nucleus with many neutrons goes against the Pauli principle. So, for example, you can have hydrogen-6 or helium-6. Otherwise, the Pauli principle prevents it. Normal hydrogen without lambda particles is only hydrogen-3, tritium, whereas hyperhydrogen can go hyperhydrogen-4, 5, and 6, if I remember well, etc., etc. So it extends very much the number of nucleons. And then, of course, this was a study of interactions between particles, nucleons, and strange particles and nucleons inside the nucleon. So it's really very important. As you see, I showed you a paper published last October. There are still many, many labs working on hypernuclei. Now they are mostly produced in accelerators, of course, not in emulsion and cosmic rays, but still it's a very active field of research in nuclear physics.
If the topic of discussion is finished, I may share an anecdote about the cognac, if I may. Pliski kept a bottle of cognac in his office, and he offered it to external guests for the Friday seminars. And he told me in the 80s that he noticed that one particular bottle had a deteriorating quality of cognac with time. So he conducted an investigation which pointed to a watchman or cieć in Polish who were usually fond of drinking. He went to him and told him, please, if you want to drink this cognac, please do, but do not fill it up with tea afterwards.
Why was the name of the V particle changed into lambda? Was there any systematics in
this discussion happened during this conference I mentioned in Bagnères de Bigorre in France. Physicists somehow came to the conclusion that keeping the names such as V01, V02, etc. doesn't make any sense, and there was a new scheme of naming of particles established at that conference. So starting approximately from the end of 1953, the V particles were never called V particles, but lambda, K, tau, etc., etc. Sigma, there were more particles, sigma, psi particles, etc. This was an agreement reached in June or July 1953 in Bagnères de Bigorre, which Danish did not attend. He was not allowed to go.
So if there are no questions or comments, so let's thank the speaker again. And I have one announcement to make. The next colloquium will be on 19th of December in quite unusual time, because the lecture will be given by the recipient of the prestigious prize by named Jerzy Pniewski and Foundation, Kościuszko Foundation. So this will be a big event. I don't know exactly whether in this room or maybe in Togo 3. It will be in the afternoon because it will be live transmitted to the United States. So just watch for the announcements exactly when and what time it will be given. Okay, thank you, and see you in December then.